Good afternoon, everyone. Carahsoft Technology would like to welcome you to our WPI Services webcast. Before we get started, I'd like to go over a few housekeeping items. All of your lines have been muted to reduce background noise. We hope you take advantage of the Q&A pod on the left side of your screen to ask questions throughout the presentation. We will do our best to answer all of your questions at the end of the presentation. If for some reason we do not get to your questions, the SAP team at Carahsoft will follow up with you offline. Carahsoft is a trusted government IT solutions provider delivering software and support solutions to federal, state, and local government agencies. Carahsoft maintains dedicated teams to support sales and marketing for all of its vendors, including SAP, Symantec, Adobe, EMC, VMware, HP, and Red Hat. Our contact information will be at the end of the presentation, so please don't hesitate to call or email us for any of your needs. This webcast is being recorded and a copy of the presentation will be emailed to you. At this time, I would like to introduce our speaker for today, Justin Woulfe, Executive Vice President of WPI Services. Justin, the floor is all yours.
Great, thanks. Good afternoon, everybody. Today we're going to talk a little bit about the optimization technology that we provide DoD, oil and gas, and many large CapEx and kinds of operations. The software is called Opus, and it's used to simplify lifecycle decisions, perform readiness analysis, and lower the operations costs of our systems. I'm going to talk a little bit about this optimization software, the cost and performance capabilities, as well as how we would use Opus Suite for decision support across the program's lifecycle. We'll discuss some of the unique capabilities, how we integrate with external data sources and other customer systems like SAP. Then we'll actually walk through a demo of the software. When we look at the optimization trade space, there's really three major areas that we want to consider to lower the operations costs of our systems and increase the readiness. The first is the technical information about the system itself. That would be the failure rates, the demand for certain types of components, the failure modes of those components, the maintenance tasks that are required to actually repair the system, for example. The second would be the support solution itself. So where do we have depots? What's the position of our vendors? Are there diminishing material shortages or tech refresh kinds of issues that we need to be aware of? And then we also want to consider some of the supply chain type metrics. This would be the transit times, the storage costs, the delay time perhaps getting from one location to another. And then finally, the operations of our platforms, getting from point A to point B, as well as the actual operational profile for the particular system. In the case of an aircraft, for example, this could be flight hours per year at sort of the highest level, or really detailed types of operational profile information, such as 2-hour sorties 3 days a week, 6-hour sortie 1 day a week, and then some 90-day surge period of increased op tempo during a training exercise. All of this allows us to understand where we are today. That would be the blue dot that you see in the center of your screen. That would show the relative cost and effectiveness, in this case perhaps availability, of our platform given today's failure rates of the components, the current support solution, the current spare parts profile, the current set of maintainers and test equipment, and the current operational. The real trade space, though, is actually moving to an optimal state from where we are today. And our goal is to either, for a certain budget, increase the availability of that weapon system or program, or for a certain level of availability, decrease the cost to reach that level, or something in between. And that's really represented here by this curve that we can see on the middle of the screen. And then, of course, as the program evolves, certainly perhaps with tech refresh, maybe we have a lower price component, or maybe we decrease the cost of maintenance activities, or maybe we just don't live up to the engineering estimates for reliability. the curve will move left or right as the program becomes either more expensive or less expensive over the life. Opus Suite allows us to perform a full range of trades. And I think the key here is to understand it's been through a full independent validation and verification. And it's actually the tool of record for logistics analysis, readiness simulation, and lifecycle costs in the UK and Australia. In addition, the defense components of 30 countries, including the US DoD, a number of commercial companies use Opus. We'll talk a little bit about some more of the customers a little bit later on. But first, what I'd like to just discuss very quickly are some of the unique capabilities that allow us to kind of take that information that we talked about on the first slide and actually do something with it. There are really three parts of Opus Suite that are designed to sit on top of some customer data set or some existing tool suite to actually optimize outcomes, perform readiness simulation, and catalog lifecycle costs. Our goal is to optimize our resources. This could be people, test equipment, tooling, dimension our facilities and support equipment, perform manpower trade studies, do enhanced level and location of repair analysis, optimize all variables over time, and provide a stochastic Monte Carlo mission simulation tool that allows us to understand how we're actually going to perform very discrete elements of time and very specific types of missions. We also provide a complete readiness-based sparing functionality with no computational limits. There's no limit to the number of items or the number of systems that you can put in your software, nor is there any limit to the amount of time that we can look at our results. We also have a complete mill standard 1388 compliant import and export schema and a GEIA 0007 compliant database structure. So we can really process a pretty significant amount of data and also a complete link up through the Microsoft ODBC interface to reach out to other types of commercial tools and database structures like SAP, different MRO tools and systems, and different types of ERP systems. And then finally, we want to sum up all of this data that we've optimized and simulated into a robust lifecycle cost analysis that's compliant with some of the DoD and CAPE standards, but then also relate cost to our KPPs, our key performance parameters. And this could include cost per flying hour, or cost per hour of operation, or cost per terabyte, or some other metric. Opus Suite has defense customers and software users, about 600 licenses installed across 150 unique customers in 30 countries. We can see just a subset of these here between the U.S. Air Force and Navy, the U.K. Ministry of Defense, really most of the NATO nations, as well as a number of support contractors. In addition to our defense customers, about 30% of our business consists of rail and oil and gas and commercial power generation. When we look at some of the programs using Opus Suite, there's a pretty broad range of defense programs across, as well as commercial aviation programs like the Airbus commercial systems, Boeing's commercial airliners, and a number of large data centers, wind-powered operations like Alstom, Bombardier trains, Hawker, commercial jets, Cessna Citation, those kinds of things. I think the key takeaway here on this slide is we also have a pretty broad basis of experience using the tools to solve really complex performance-based logistics problems. This is an area where we really have a lot of experience, and we've really done a lot of upfront work in showing customers that it is possible to enter into affordable performance-based logistics contracts that achieve desired outcomes and actually reduce costs. We'll talk more about that. When we look at the reasons for loss of operations in our systems, really it comes down to really a number of areas, but in this particular case, it could be accidents and unforeseen events, a lack of spare parts, maybe poor maintenance planning, perhaps it's resource shortages, or maybe it's just the inherent system and component failure. And if we want to get the most bang for the buck, we need to understand in what particular area we need to invest to improve the reliability or change the maintenance concept, purchase more spare parts, maybe get the right tooling or documentation or other resources. What Opus Suite allows us to do is identify exactly that logistics element that contributes to downtime so that we don't invest in an area where we're not going to get a return. When we use Opus Suite for decision support analyses, one key area that we look at is the location of repair and optimizing the number of resources. We've actually done quite a bit of work in this area, and our customers have actually reduced their maintenance costs by more than 20%. And this involves optimizing both the quantity and location of people, the quantity and location of support equipment, and optimizing the repair strategy by location, by maintenance task, and by failure mode. Then we'd simulate outcomes and identify solutions when customers are faced with key kinds of what-if issues. Perhaps it's an investment in a reliability growth program or standing up a new repair facility. Does that investment pay off, and what's the ROI? And that's a key kind of challenge that Opus Suite is used to solve. Next would be looking at the system's operations, the readiness, and our lifecycle cost analysis. And our customers, especially in the UK, have had a lot of experience with this and have shown that it's possible to reduce their operations and maintenance costs by double-digit figures. On the Merlin helicopter program, they were able to lower their costs by more than 15%. On A400M, they used Opus Suite to lower the PBL contract cost by about 35%. And this involves comprehensive decision support and performance modeling, optimizing the manpower, the spare parts, their maintenance resources to a desired availability level, all at once in a single model to achieve some outcomes. And this would be looking at not only platform availability, but also the mission time and the time-dependent factors of how availability of people and resources and the system utilization itself varies over time. Then this all comes together to create a holistic cost and performance modeling to truly optimize our results. By considering all aspects of our program and all aspects of our system, not just one particular area, we're able to lower our lifecycle costs substantially, demonstrate return on investment of investment initiatives, look at things like our key performance parameters, our sortie generation rate, the logistics footprint, our cost per hour of operation, and actually show that the way that we're operating is actually cost effective, and also show the impact that things like budget cuts will actually have on our readiness. We don't just have to hypothesize that a budget cut would actually be detrimental. We can show how every dollar taken or invested in the program could result in some level of readiness. So when we look at Opus Suite, there's really an iterative developmental process to create a model. You don't have to start with all the data and all the information that you will eventually have in a really robust, really complete model. One thing that we've really tried to focus on is the ability to iterate models and continuously develop them so we can get past the concept of analysis paralysis. We really want to have people start building models as early in a program as possible, and that means that they may not have really good data. They may have really rough data. And so as they move towards completing their models, we want them to take that rough data, start building models, and continuously iterate them to understand what data is important, what areas drive the result, then focus on those areas that actually impact the outcome. When we look at some of the basic input parameters, these are things that most programs have readily available. They have their item IDs. Maybe that's an LCN number or just a part number. They have some measure of demand or failure rate for that component. They know what it costs. And they know about what it costs to repair or order a new item in the case of a consumable item. They have some sense of the system duty cycle. That could be just op hours per year, or maybe in the case of a data center, how many cycles per year. And then they know about what it takes to repair the system, about what it takes to repair the items. And they have some concept of how long it takes to ship systems or ship parts between locations. This really basic set of information, even at its roughest level of input helps us to build really good foundations from which we can continue to incrementally refine our models, build really robust models that would pass, perhaps congressional scrutiny, for example. And Opus Suite's there throughout that whole process, help us iterate those results. When we look at how we integrate with some of our data sources, there's really kind of three kinds of data. You have predictive data, maybe from an engineering team. You have cost data, and then you have things coming out of our MRP systems, our logistics management planning systems, or our ERP systems like SAP. And the key is to import this data directly into Opus. We have a really robust data import and export mechanism that we'll discuss. Opus will then process that data, generate the master data files, identify those areas where there's incomplete information, analyze the data, look at the operations, maybe include previous Opus 10 or Symlox results to compare to where there's improvements or where there's been degradation in the results. Actually optimize the scenario and optimize the outcomes, perform the analysis, and then feed that data back into the system and actually allow us to impact our operations and reduce the overall lifecycle cost. With that sort of basic introduction, I actually would like to step into the tool itself. I think that's really the most effective way to kind of explain some of this information. There's more slides in backup, and for those of you that are interested in learning more about the bases behind the tools, I'll be more than happy to provide those slides, and I think the Carahsoft folks have those available. So, and if anybody would like to follow up afterwards, please reach out to Dustin to get those additional backup slides in back. So the first thing that we're going to look at is a basic Opus 10 input file. And I'll talk everybody through this. When we look at a basic input file, what we typically focus on is the model view. And here in this particular model view, we're going to look at a ship system that consists of 5 Corvette-style ships. They're going to be deployed in these 5 different locations that we can see here, supported by 2 regional bases, a main depot, and a contractor or OEM workshop. You can see here the support organization has transit times to and from, and there's distributions around these. When ships go to sea, for example, it doesn't necessarily take a fixed amount of time. There's certainly a time distribution around that. And then what we can see here in our item structure is every item in the system has some repair information and level of indenture within the system. You'll also notice there's some different colors here. Those boxes that are orange indicate the systems and subsystems. Those areas that are gray are assemblies, and those that are yellow are repairable items, and those that are blue are consumable throwaway items. If I click any one of these individual items here, we can see the repair concepts and preventative maintenance information and corrective maintenance information for every component. Just to show here, we have one of these generators installed on each ship. We have generator repair, both for corrective and preventative maintenance happening at the individual bases. We have some repair happening on the ships, and then the majority of the repair activities happen at the main depot. And we can go through every one of these items, and you can see the different repair concepts. And we allow users to either build these tables graphically through the user interface, import the information from some external database, or just enter the data directly into the tables themselves. There's a few different ways to get this type of information. Additionally, if I were to click on the item table, for example, you can see that we have some individual unique part numbers, descriptions, which is an optional column, unit prices, failure rates, and whether something's repairable or consumable. Going back to the model view, we can look at some other interesting things. I'll resize this window and open up one of these. We can see that we have some deployment information where we have quantities of chips per site with the relative utilization. And from this, we can understand perhaps what the level of availability that we'll achieve with each system would be, and how we can expect to maybe support the system effectively. The other thing that we might be concerned about, especially early on in the systems phase, is how the supplier and the supplier suggestion or the provided solution would actually come back to impact the overarching cost and availability. Sometimes our suppliers may not recommend the cost optimal solution. That would require us to actually evaluate their effectiveness. So the first thing that we'll do is look at a given supplier solution. We can see here in this particular scenario, the red dot on the center of the screen indicates that for an initial 2 years spare parts package, we would achieve a 69% availability, and that would cost about $55 million, or about $10 or $11 million a ship. Now, this would be the supplier suggestion. And so we may or may not believe exactly what that supplier says, and if we were to purchase this without any additional evaluation, that might not be the best path forward. We'd certainly want to have the ability to evaluate how effective that solution is and what we could expect to get from that from an availability perspective. So what we can do is, instead of running this analysis, and I'll show you how this runs, we can actually just run our own and say, well, we're going to disregard the contractor's solution, and we're going to optimize these results and actually generate our own curve. And that shows the graph that you can see now here. We still have the original solution shown and graphed on our screen, but then we also have this orange curve, and the orange curve shows us that perhaps the contractor recommended solution might be profitable, but it's certainly not optimal. We can see the difference here. If we were willing to spend the $55 million, that the potential cost impact for achieving that $55 million budget would be about a 17% difference in availability. So if we were willing to spend $55 million to support our weapon system, we could potentially achieve not a 69% availability, but an 86% availability, and that's pretty substantial. Alternatively, if that contractor provided a sabot was actually the requirement, it's possible that we could save $32 million, really cut the operations of that spare parts package cost in half through optimization. And really, maybe the correct answer, or the answer that might be most advantageous, would be somewhere in between. So maybe achieve some increased level of availability and some level of reduced cost, and we can really pick any point along the curve and understand both what the availability is, but also what the cost impact is. And in this case, we'll pick the point that's close to the 80% availability target. And you can see that compared to the supplier solution, not only will we achieve a higher level of availability and readiness, it will also reduce our lifecycle cost for these spare parts by almost $20 million. Then we can compare what those individual deltas are between the spare parts packages. What we can see here is the list of the spares and the relative differences across the operation. And we can see that in this first view, we'll rank order the delta from high to low, and we can see that we're going to buy a completely different mix of spares than what the supplier suggested. We're going to have quite a few spares at the individual bases, and then also take away spares from other locations. And the net result of this buying a different mix, so many less of some and a few more of others to achieve the desired level of readiness, results in that $20 million difference and almost 11% increase in availability. There's a lot of other metrics that we can look at. If I go back to the graph, this graph here shows availability. There's also a lot of other measures of effectiveness that programs might use. You could look at the amount of annual downtime. You could look at the amount of downtime due to corrective maintenance, the amount of downtime due to preventative or scheduled maintenance, the number of back orders, our risk of shortages, the waiting time for parts, etc. So there's really a way to kind of slice and dice the output data and the optimization to really show any stakeholder exactly the metric that they need to see to feel confident in the solution. So for example, if we were to look at the mean downtime, we can see that in the contractor recommended case, we would have about 64 hours of downtime per downing event. And in our optimal case, we would have about 30 hours of downtime per downing event. We'd cut the downtime in half. If we were to look at the time that we were down, or maybe we'll look at the risk of shortage, we can see in this case that we reduce the risk of shortage substantially as well. So that would be the chance of turning around and not having a part available. It's actually quite high in the contractor solution, and it's been reduced significantly here in the Opus. We'll go back to the availability chart. Then also we can begin to start running excursions. So again, we're still using a snapshot of the data. Maybe there's a chance that we could increase the op tempo of our systems, use them more. Maybe we deploy systems to new locations. Maybe we need to have a different mix of systems, or maybe we perform some tech refresh. And so what we can do is very quickly, if I go back to the original model view, we can see that we have 3 systems or 2 bases with 3 systems deployed, supported by 1 base, and 2 ships deployed and supported by a second base. Maybe we change that site profile and move to a slightly different structure, where maybe we deploy a system somewhere else in the world, and it's supported by its own regional depot or own regional base. 2 systems would be supported by another base, and the 4th and 5th system would be supported here. And we can see now what the impact of this change in deployment is to the optimal outcome. You can also see that we increase the op tempo of ship number 3. We really double its utilization. And now we can see what the re-optimization of this would look like. And we can see that this particular scenario, we increase the operations costs just a little bit from the baseline scenario, where were we to go with the spend that $55 million budget, in this case we would only, that redeployment, that increased utilization would result in about a 13% increase from the contractor provided solution. And if we were happy with, when we compare optimal solution to optimal solution, what we can see is it actually increased the operations costs quite substantially. So while we might be using that 80% availability target that we were looking at in the optimal case, we can see that redeploying a system and increasing its utilization results in about a $13 million difference to our operations cost. And we can do this for any number of initiatives. Right now in the Joint Strike Fighter program, we're doing this for the reliability and maintainability program as they start to look at increasing the reliability of the aircraft. They're using Opus Suite to evaluate the relative return on investments of different reliability improvement program initiatives. For example, if I wanted to improve a particular component and there was some amount of investment required to do so, we would use Opus Suite to show, would that investment and potential outcome actually result in some net savings to the program or some return on investment, and what is that return on investment? And then after that initiative is implemented, what's the long-term life cycle cost implications and cost per flying hour to all 3 variants of the aircraft, all of our international partners, at all the different. Once we've decided on an optimal solution, We then might want to run some different simulation results and understand how the system will actually perform in some different mission scenarios. And what we'll look at here in this particular case is how we have different types of partially mission capable types of analyses run. For this ship system, for example, we may want to simulate our outcome where we would be focusing on a particular scenario set where we have some partial mission capability while we're at anchor or while we're at some level of transportation, and then perhaps maybe have a different set of requirements when we're engaging a target or conducting surveillance or something like that. So we'll just analyze the single ship using the same data set from before and actually now start to dig into some of the different components, actually understand how their relative utilization will actually impact the readiness of the system depending on the desired set of missions that I need to do. So if I go down here, we can see all of the different propulsion mechanisms here within the system. We can start to look at how our individual system utilization will actually result in some amount of readiness in the platform. So we can see that we introduce a new concept here called the reliability block diagram. And in these reliability block diagrams, we would actually import these directly from our MRP system, maybe from our reliability tool sets, where we would categorize not only the cost, but also the individual configuration of our system. We can see some of that information over in the item structure. We can see that we have the full system breakdown coming out of our material planning systems. And then also, if I go here to the RBD tables, this is actually an import directly from our reliability tool suite to actually take this reliability block diagram information and utilize it in the optimization simulations. If I go back to the model view, we can then start to dig through this, and I'll show this graphic. We can see how this all starts to come together. And we can show how the relative RBDs are actually implemented here within the tool. So we can see that we have reliability block diagrams implemented for component part 4013. So I can just find that. And we can see that we have this reliability block diagram implemented for the navigation radar system. With that tree. You can see that in the default case, we have a very complex reliability where we have these different components. Only 2 out of the 3 is required for the lower tree. 6 out of the 7 are required for the upper tree. And that's really the standard utilization of that particular system. We can see how these RBDs kind of come into play to implement things like redundancy within our platform that allow us to actually build a very complex views of how the system will perform in different types of operations and what's actually required to operate the system. If I go to the RBD bridge, we can go to component 4011. Again, I can use the search function 4011. And we can see that it's there, and we can see that we have this bridge that's built with 5 different components where some segment of the tree has to be in the basement. Again, this is coming straight out of our reliability tool. If I click simulate, we'll conduct a stochastic Monte Carlo simulation. In this case, we'll run 600 replications to get the desired confidence. We can see that when benchmarked against other simulation tools like Crystal and other things on the market, we're about 100 times faster of a simulation engine than Crystal and many, many times faster, maybe 20 or 30 times faster than some of the IBM. We can see here in this particular set of results, when we look at the number of systems that are on mission, the little blue line at the top shows the systems that are in active repair. some level of readiness and some level of mission utilization. When we look at how systems are assigned, we can then click through some of these different things, and we can see that we have maybe look at the number of repairs happening at each given hour within our simulation. We can look at the number or the amount of system downtime. And we can see how we accumulate mission time over, in this case, the 80-hour simulation. The gray line that we're seeing here would show the percentile level that we're interested in. In this case, we'll look at the 90th percentile. So at a very high level of confidence, our expected system time would actually drop. If we were to look at the total, we can see that we'll achieve 74.36 hours of system time out of the requested 80. And at the higher confidence interval, that really sums up to about 6 hours. There's a little bit of risk in our solution. To go back to the mission results, we can then start to look not only at system time, but also the mission effectiveness. We can see here again, if we were to look at the total, that we would achieve about 94% of our mission results, and this would be the mean, and at that higher confidence interval, we'd achieve about 86%. And we can see the difference here between mission time and actual system availability. We can see here in the system availability case, we have a very high availability, and that doesn't, though, necessarily correspond to the same amount of mission time. And there's a slight difference there between having a system be available and having it be mission capable. And that has to go back with the reliability. Some of our operations research analysts then also dig into some of the individual item results, look at the failures and number of demands by item, dig down into this type of information and look at, perhaps the waiting time. We can see that we don't have any waiting time for parts in the model. We certainly have demands, and we certainly have some different stock levels and items on it. They might also look at our resource results and understand how our people are being utilized, look at some of those different factors. And then they can also have the ability to dig down into the underlying data that's behind this graph to actually see what's happening within each replication, see what the risk is across some of the different factors, and actually understand, what's the highest probability of outcome. Dig down into those files. This information would then feed our lifecycle cost model. So we've done the strategic types of optimization. We've done some tactical simulation. And then we're really concerned with the overarching lifecycle cost and the sensitivity of that lifecycle cost to our input. Again, you'll notice our input data here is exactly the same here in our input stream. So we're using the same tables. We're just taking another look at it within our issue. We can see here from our model view that we now have the imported work breakdown structure that we desired from our customers, and data from Opus and Symlox directly feeds our WBS. We can look at the results of this. We can see here in this case, I'll shrink this as well, within our WBS, that the total lifecycle cost of our system would be about $455 million over its 10-year operational cycle. Remember, we originally dimensioned 2 years of spares. We did some additional simulation, and then we increased the life length of the system to account for the rest of its useful life. And we might want to understand how this actually kind of plays out across some of our different cost elements. So I can just expand those out here. We'll graphically update. We'll be able to see that in this case, we'll spend about $250 million acquiring the systems, another $28 million acquiring spares for the system, of about $109, almost $110 million in operations and recurring costs, another $56 million in yearly operations. Then there's a small sliver of green there that I can zoom in on. And we can see that we also have about $10 million in termination costs at the end of the year. I have 5 different dimensions that I can begin to use to actually look at how these costs are spread across the different components in the system, over time, different tasks. full set of sensitivity analyses, and different resource and station level results. If I drag time over to the x-axis, we can see that in this particular case, the majority of our money in acquisition is spent in the first 2 years of operations. Then we have operations costs every year thereafter. Right, I'll go back to my LCC tree. I can always remove that acquisition cost piece and just focus on those other cost elements. This will allow us to look at, and we can see we show the remainder here, and I can always hide that as well. If I were to go to time, and we can see that we have in year one, if we take the acquisition cost out, we just have some recurring costs and yearly operations. And then we're actually showing the net present value for that investment over the next 20 years of operations. Then we have the termination cost at the end. If I drag time back, and we can also look at these in a pivot table format. I know probably over the DCO and the web link there, the numbers could be a little bit hard to read. So we can always just open a tabular view and we can see the different cost elements that we're looking at by year across the model. And if I scroll over, we can see there that termination costs all happening. If we go back to the bar graph, there's not a lot of other different kinds of views that we can take. If I drag time back, perhaps there's sensitivity around some of the different elements in our model. And if I were to open the sensitivity pane, we can see here in our model that the sensitivity that we're concerned about in this particular model has to do with the price of the component. And there's a risk that the components could be 20% more expensive than we were planning for. If I drag the sensitivity piece over here to the x-axis, what we'll do is we'll show the baseline price and then also the sensitivity to that particular price component over here in the sensitivity. So we'll be able to compare what would happen if we had realized that particular piece of sensitivity. If I zoom in on this, we can see that there's about a 5% potential for a 5% increase in the recurring costs and a 16% increase in our total investments through that 20% increase in the price of my components. And we can do all kinds of multivariate sensitivity analysis, single-variate sensitivity analysis, and nonlinear types of sensitivity analysis as well. With really detailed lifecycle cost estimates that take full levels of risk. Cancel that soon. I'll drag the sensitivity piece back. And we can also look at some of the material cost drivers within our system. We can see that the ship itself certainly has a lot of additional expense, especially around operations. But then maybe we want to look at the operations cost for some other components within our system. Here we can see that we have some rotors, we have some turbine components, and some other different switches and platform systems themselves that have some fairly high recurring costs that might be candidates for cost reduction initiatives or maybe to be implemented in some kind of cost war room activity. If I drag material back, we can also look at the resources in the model and understand where we have money being spent, and we can also look at the individual stations in our model and see where the different dollars are being spent both on the individual ships, but then also at our depots and our bases. And so we can see the recurring costs here. We have a lot of repair activity happening at the depots and at our bases. That would be where the majority of that repair cost would be, and then we have operations costs, on the individual ships themselves that drive costs there. If I come back here to Opus, we'll look at all of the costs in the system, include that acquisition cost again, and this will now dynamically update to show that, in fact, we have a lot of acquisition costs on top of our yearly operations and termination costs for the individual ships themselves. So we can really split the costs any different way. We have a lot of different functionality and a lot of different capability. And some of you might have noticed the divisor here on the top. And in this case, we'll look at the op hours per year. So we're looking at total cost, but we might also be interested in the actual cost per hour of operations. And we can look here and we can see the relative cost by location for an hour of operation. is something that is typically used as a key performance parameter on our system. So a lot of different ways to split costs, look at costs, and evaluate cost effectiveness. Of course, it's very easy to continuously iterate these models, generate new results, run a full array of what-if analyses and what-if scenarios to actually ensure that we're achieving the desired level of readiness that we want at the lowest lifecycle cost and with the appropriate level of risk. This creates a very defensible, robust analyses that we can use to ensure and show our program managers and those within the OSD or at the congressional level that we are actually operating efficiently, we are actually operating effectively, and we're doing everything that we can to be good stewards of the taxpayer. With that concludes the demo. So I'd like to turn it over at this time to Q&A and answer any questions that folks in the audience have.
Thanks, Justin. We had a couple questions come up. The first one is, what programs in the DoD are using Opus Suite and for what?
Good question. So within again, we are supporting the weapon systems and programs of 30 countries' DoDs, including the U.S. Air Force, the U.S. Navy, and now actually some U.S. Army programs. We are supporting the F-35 program and some of their cost reduction initiatives in the cost war room. So that's a big one. We're also supporting a number of Navy and NAVSEA programs, including the EPLM, so the Product Lifecycle Management Integrated Data Environment. That includes some ship systems. That includes some rotary wing systems. And it also includes some Army land systems and Marine Corps land systems like LAV programs. Additionally, we also do some work with some data centers and C4ISR platforms with this
And another question we have is, what type of skill set training is required to use the tools?
Sure. So, this may have been a little bit overwhelming for some of the folks. There's quite a lot of data and quite a lot of manipulation that can be done by an analyst. But I think the key here is it's all very graphical. It's all very GUI-driven with a lot of complex math behind it. But the analyst doesn't necessarily have to have they don't have to have an operations research. Our training courses for logisticians and systems engineers is a 4-day training course for, I'll say, preliminary tool suite utilization. And then typically we'll do that basic course and then a follow-up course some number of months later to teach more advanced. So really with the 2 weeks of training over the course of maybe a 6-month utilization period, an analyst should be fully functional and able to use the tools in a fairly expert manner.
The next question we have is, how would these type of tools apply to other program types besides aircraft, like data centers?
Yeah, so really anytime you have a large capital expenditure, it's a good time to start evaluating cost and effectiveness. If we're focused on very low-cost items or lots and lots of consumable things, maybe that's not the right utilization of these kind of decision support tools. But particularly in a data center environment, for example, even though it may not look like a traditional kinetic weapon, it certainly is very expensive and very complex, has many failure modes, has certain types of manpower requirements, certainly has tech refresh issues, so you want to plan for that, and certainly have relatively high life cycle costs of operations. And so really a data center is just another type of capital-intensive system that can benefit from these types of decision support.
Great, thanks, Justin. I think that's all the questions we have for today. So I want to thank our speaker, Justin. And at this time, if you have any questions, I'm sorry. I'd like to thank all of our participants as well as Justin for being with us today. We hope our webcast has been helpful for you and your organization. If you have any further questions or like to request more information, please feel free to contact the SAP team at Carahsoft. Our contact information is and will be displayed on your screen, so please don't hesitate to call or email us. Thank you and have a great day.